Chapter 10, the t-test for two independent samples, Part 2. In this video, I'm going to walk you through an example of a non-directional hypothesis test using the t-test for two independent samples. So in our text, example 10.1 presents the following information. Research results suggest a relationship between the TV viewing habits of 5-year-old children and their future performance in high school. Researchers report that high school students who had regularly watched Sesame Street as children had better grades in high school than their peers who did not watch Sesame Street. Suppose that you as a researcher intend to examine this phenomenon using a sample of 20 high school students. The first step of our hypothesis test requires that we indicate what our research and null hypothesis are before we collect data. So the null would state the following. Again, the null always indicates that nothing is happening or there is no difference between the populations that we're comparing. So we would state there is no difference in academic success between high school students that watched Sesame Street as children compared to high school students that did not watch Sesame Street. As children. And then we must also include the proper notation. So again, one population is going to represent those who watched Sesame Street as children. The other population represents those that did not. And of course, we're going to take samples from both of those populations to test this hypothesis. But what we are hypothesizing is that the population, and I'm just going to subnote it with a W, that did watch, minus the average of those that did not watch. So again, the W is for those who watched, DW did not watch, is equal to 0. Or we could say that the average high school success score for those who watched is equal to the average success score for those who did not watch. So again, the null says no difference. We will not see a difference in the academic success of high school students based on this difference. Next, we would state the alternative or research hypothesis, what we're interested in. And just to save some time and writing, I'm just going to put that there is a difference. Again, using the previous statement as a guide, we would simply express that there is a difference in the academic success between high school students that watched Sesame Street as children compared to the high school students that did not watch Sesame Street as children. So there is a difference, and therefore the notation would read as follows. So the average success scores of those who watched minus the average score for those who did not watch is not equal to 0. We don't expect them to be the same. We expect them to be different. Or we could write the average score of those who watched does not equal those who did not watch. So now we've established what we're testing. Again, we're going to test the null hypothesis that says there's no difference. And we would expect that mean difference of 0 to be in the center of the distribution of sample mean differences if we were able to collect all the random samples from the population. step 2 requires that we set the criteria for our t-test. But before we do so, let's get a little bit more information about the research scenario presented in example 10.1. So the researcher first surveys the students' parents to obtain information on the family's TV viewing habits during the time that the students were 5 years old. Based on the survey results, the researcher selects a sample of 10 students with a history of watching Sesame Street and a sample of 10 students who did not watch the program. So total, we're working with 20 individuals, but notice how they've been allocated into these different conditions. So half, 10 of them, represent the population that watched Sesame Street, and 10 are representing the group that did not watch. So at this time, we know that we can calculate the degrees of freedom which is needed to set our criteria. So let's do that. So again, we know that our first sample, which is those who watched, we have sample 1. And again, sample 1, just so you know, is the group that watched the Sesame Street program. We have 10 individuals. And then we have our second sample. And let me just put the heading above. Okay, just to clarify, so the watch category, we had N sub 1, it's just our first sample, was equal to 10 individuals. Our second sample were those who did not watch, and we have 10 individuals. So we're going to calculate the degrees of freedom. And we learned that a degrees of freedom is equal to the first degrees of freedom for our first sample, added to the degrees of freedom for our second, which is the same as saying N1 minus 1 plus N2 minus 1. So we'll replace variables. Our sample size for the first sample is equal to 10 minus 1 plus 10 minus 1. So we have 9 plus 9 is equal to 18. And now we have the degrees of freedom that represents the combination of both samples, which will now enable us to find our critical T. So again, our second step is to set the criteria. Additional information that's important is that we were told to conduct, in this example, a test where alpha is equal to 0.01. So now we're going to utilize our t-table to determine what the critical t-value is equal to. And we'll draw it out. Again, in the center, we have the null that says population 1 average minus population 2 average is equal to 0. We expect no difference between the populations of those who watched Sesame Street as children compared to the average success scores of the population of those who did not watch Sesame Street. So now we're going to set the criteria using our t distribution. We're going to find out what that critical t is equal to above and below the center value of 0. So here is our t distribution. Again, we're conducting a two-tailed test, so we're going to focus on this tier at 0.01. So there's our alpha level. Our degrees of freedom over here was equal to 18. So here is 18, and we're just going to see where those values intersect so that we can report our critical t. And we find that our critical t is positive negative 2.878. So now we can identify the critical region set by negative 878 and positive 2.878. And we'll come back to this diagram after we calculate our T statistic. So next step 3, is to compute our T statistic, and that actually requires a lot of other statistics. So we're going to start with the mean, the sum of square deviations for each distribution, and then calculate our T statistic. So I've taken the data that was presented in the text, for example 10.1, and created a small little Excel worksheet where I simplified some of the math to save a little bit of time. So first, we recognize that the group on the left represents sample 1, and we have 10 individuals. Sample 2, we also have 10 individuals. And now we're going to calculate the mean. These were given, but I want you to all be clear as to where these values are coming from. So sample 1 average, so again our equation back from chapter 3. So the sum of all scores, I've identified all the scores here, and down here is the sum of our x values for our first distribution. So that's equal to 930. And we know that a sample size is equal to 10. So the sample average for our first group, it would be 930 divided by 10, and we get an average score of 93. So again, these students have been identified as being part of one of two groups, those who watch Sesame Street versus those who don't. And then they were given an assessment at the high school level, and that assessment produced a score. And so these are all those 10 students' scores. Collectively, the average of all those 10 students is equal to a score of 93. Similarly, we'll do the same with our second distribution, so the average of x sub 2 over n2. So here are all the scores for those 10 individuals, and this represents the average, the sum of all those 10 scores for our second distribution. Let me just, sum of x sub 2 is equal to 850. And we have 10 individuals, so the average score for these high school students that did not watch Sesame Street as children is equal to 85. So at this point, it's important to note what we're testing. The null says that there is no difference. Numerically speaking, we see a difference. And so now what we're going to do is determine if that difference between 85 and 93 is statistically significant. If 85 is somewhat close to 93 in the distribution of sample means, then there's no difference. And this difference was solely due to chance. But if this mean difference between these two samples is out in the tails, then we would conclude that the difference is significant, and the difference is as a result of the fact that one group watched Sesame Street and the other did not. Next, we're going to calculate the sum of square deviations for both distributions using the computational formula, simply because it's faster, saves us some time. So our equation is the sum of x squared minus the sum of x squared over n. And we're going to replace variables for our first distribution. So the sum of square deviations for our first distribution is equal to, and I should indicate the second column here, I've already squared all these x values, again, just to save time. So I took 86 and I squared it, 87 and I squared it. And so now I have all of the x values that have been squared, and the summation is this value here, and which would represent this value. And the sum of x represents this in the parentheses. So I have 86,690 minus 930. We're going to square that over 10. So in your calculators, go ahead and square 930, divide by 10, and subtract it from 86,690. And what we should get as a final sum of square deviations for our first distribution is equal to 200. And again, that value was provided in example 10.1, but I want you to see all the math that goes into producing these statistics so that it is clear and you just don't rely on these given values, that you know how to compute these on your own. We're going to do the same with the other distribution. So again, I've taken all the x values for our second distribution of those who did not watch Sesame Street, and I squared them. So 90 squared gave me 8,100, so on and so forth. So then all of these have been squared, and here's the summation of those squared values. And again, as we saw with the mean calculation, that's the sum of x. So I'm going to replace variables again, given our equation here. So the sum of all x values that have been squared is this value here. So that's 72,410 minus the sum of x, which would be in the parentheses, 850. We're going to square that. Our sample size is equal to 10. So in your calculator, take 850, square it, divide by 10, and subtract it from 72,410. And what we should get here is equal to 160. So now we have the sum of squared deviations for both distributions. We're going to need that to calculate our pooled variance so that we can then compute the estimated standard error of the mean difference and also enable us to calculate our T statistic. So again, these values were given, but this slide hopefully clarifies where those values are coming from. So ultimately, to calculate our T statistic, our equation is M1 minus M2, which we just calculated, minus, so that sample mean difference, minus the population mean difference, which comes from the null, over our estimated standard error of the mean difference. And in order to calculate this, again, we do have some values right now. So let's go ahead and replace what we do know. So we know that the sample 1 average was equal to 93. And our second sample mean, so 93 minus 85 minus, and we've indicated that the population 1 minus population 2, that's representative of the null hypothesis that states there will be no difference. So that's equal to 0. Again, don't omit that from your equation. You still need to include it. And what we don't have is the estimated standard error of the mean difference. So what is our equation? Our equation says the estimated standard error of the mean difference is equal to the square root of these two fractions. So our pooled variance over n for our first sample, and the pooled variance over n2. And again, in this case, we did have equal sample sizes. In the real world, that's unlikely. But regardless, we should always rely on the pooled variance equation instead of just using variance, because we don't always have to think about, oh, are they equal in size? If they're equal in size, you can still use pooled variance. So now we know that we need to calculate our pooled variance. So our pooled variance equation is SS1 plus SS2, sum of squared deviations, over degrees of freedom 1 plus degrees of freedom 2. And now we can calculate this. Again, we do have an alternate equation for pooled variance that was presented in the previous video, but given the statistics that we were provided or had to calculate, it makes more sense to use this equation because we just calculated SS. And calculating variance, which is needed for the alternate equation, would require one more step for each distribution. So in order to save time and be more efficient, we're going to stop with the variable that we just calculated, in this case SS. So we just calculated that in the previous slide, and SS1 was equal to 200, SS2 was equal to 160, and degrees of freedom for our first distribution, 9, second distribution, also 9. And so now we have 200 plus 160, so that gives us 360 over 9 plus 9 is 18. And our pooled variance, so in our calculators, 360 divided by 18 gives us a pooled variance equal to 20. And now with that value, we're able to calculate our estimated standard error of the mean difference. So we can use this value, right, to replace variables in this equation here. So now we can say that the pooled variance is equal to 20 over our sample size, which was equal to 10, added to 20 over 10. Again, notice that they're separate fractions opposed to what we saw in the pooled variance, where we take the sum of values in the numerator and divide by the sum of values in the denominator. Here, they're separate from one another. So we can calculate what these fractions are equal to, so 20 over 10 gives us 2 plus 2. And I'm going to move on down here since I have room down here. So again, estimated standard error of the mean difference is now equal to 2 plus 2, which is equal to the square root of 4, which is equal to 2. So now we've calculated the estimated standard error of the mean difference. And again, by definition, that indicates that on average, we would expect the sample mean difference, which is M1 minus M2, to deviate or differ from the population mean difference, mu1 minus mu2, by 2 points. So again, in the center, we have what's represented by the null, mu1 minus mu2 is equal to 0. And now we're saying the estimated standard error of the mean difference is equal to 2 points. So we would go up 2 and down 2. And that would represent the average range that would be normal for the difference between sample 1 and sample 2 if theoretically we had access to all samples and can produce the mean difference of all those samples. So again, the null is set in the center. We expect 0 difference between these populations. And if we take sample after sample after sample after sample and subtract the difference between sample 1 and sample 2, that the average difference or expected difference from that center would be 2 points. And so that's setting kind of the common region. Anything that falls within that range is considered common. All right, so next what we can do is use that value that we just calculated to put into our T equation. So I'm going to erase most of this so we can calculate our T statistic and then refer back to our critical T. So now we know that the estimated standard error of the mean difference, we just calculated that, was equal to 2. So now we have, whoops-a-daisy, we have T is equal to 93 minus 85 is equal to 8, and our estimated standard error of the mean difference is equal to 2. So our T statistic is equal to 4.00. Now, given our critical T value that was determined earlier, so again in the center, the null says no difference between these populations, no difference in academic performance, whether you watch Sesame Street or not. We set our critical region, given alpha of 0.01, and our critical T from our previous slide was equal to negative 2.878 and positive 2.878. And our mean difference, which was converted into a T statistic, again, that's what we're doing, is taking that mean difference and converting it into a T statistic, is equal to 4, and it's a positive 4. Positive because those who watched Sesame Street scored higher than those who didn't. And so according to our normal number line, 4 would be out over here. Again, this is our critical region. Our T statistic falls in our critical region, and we're quite happy. Again, the mean difference in terms of sample minus sample was equal to 8. And when we convert that into a T value, 8 is the same as 4.00. Again, that 8 came from M1 minus M2, which was 93 minus 85, and that was equal to 8. So again, I keep that at that number line because here in the center, mu1 minus mu2 is equal to 0. So there was an 8-point difference between what the null stated and what we observed with our sample data. And we converted that 8-point difference into a T statistic, and it was equal to 4, and it's well into the critical region. So at this point, we know that we are happy. Given our hypothesis, we get to reject the null hypothesis. The difference is large enough for us to do so. And now what we're going to do is discuss the measures of effect that we can apply to support this concluding statement. Again, step 4 is to draw your conclusion. So our preliminary conclusion is that the difference between those who watched Sesame Street as children and those who didn't in terms of their academic success was statistically significantly different, and our data supports that, and we're going to bolster those conclusions with measures of effect, including estimated D, R squared, and compute a confidence interval as well. So measuring effect size. If the null hypothesis is rejected, the size of the effect should be determined using either Cohen's d or a percent of variance explained, which is R squared. I would even recommend that even if you don't reject the null, calculating measures of effect help us illuminate whether type 1 or type 2 error has been committed. For example, if we rejected the null hypothesis in this case, as we did with a t statistic equal to 4, and our measure of effect size, for instance, our Cohen's d, perhaps, let's hypothetically say it was equal to 0.02, illustrating very low effect, then we would be led to believe that perhaps it committed a type 1 error. We said there was an effect when there really was not. In this case, it's unlikely because our sample size was so low. Again, type 1 error, type 2 error may be as a result of very large sample sizes or very low sample sizes, or small, I should say. So here's our new equation for estimated D, or Cohen's d. We take the estimated mean difference given our sample, and that's the same as we've seen in the past. But in the past it was m minus mu, but now we're working with one sample, one independent sample versus the other independent sample. And we divide by the estimated standard deviation. So just a quick review, when we have variance, our standard deviation would be the square root of our variance, right? And so here we see that what they're doing is reporting the square root. This here is the square root of the pooled variance. So in the previous chapter, chapter 9, our estimated D was equal to m minus mu divided by the standard deviation of the sample. So again, we don't have the standard deviation of the samples. We didn't calculate that, but we did calculate pooled variance. So again, knowing the relationship between those variables will help you understand the denominator of this equation. They're simply taking the square root of the pooled variance. So I could express this just to make it a little more clear. I could say the square root of the sample variance, and hopefully now you can see the equivalency between these equations. So we're going to use that equation to compute Cohen's d, and then we're also going to compute R squared, which again is expressed as the percentage of variance explained by the treatment or difference in quasi-independent variables. And this is a good question to pose here. Are we administering a treatment in this research, or are we comparing a quasi-independent variable that's expressed in two different conditions? If you answered that it's a quasi-independent variable, you're correct, because again, we're not administering treatment. We're not saying we're going to take these 5-year-olds and have them watch Sesame Street and then contact them again in high school and measure a difference. We are actually dividing these two groups based on whether or not they watched Sesame Street as children. So we're allocating them into these different categories based on a quasi-independent variable. Yes, they did, or no, they didn't. We have no control of allocating them into these different groups. They will self-allocate into these groups based on their history. So our equation has not changed from the previous chapter. We're going to take our t statistic, square it, and then for our denominator, we'll take our t statistic squared, added to degrees of freedom. And the degrees of freedom is for the combination of both samples. Okay, so we'll begin with estimated D. Our estimated D equation says we're going to take sample 1 minus sample 2 average and divide by the square root of the pooled variance. And we have all of these values. All we need to do is replace variables. So we know that sample 1 average was equal to 93. Sample 2 average was equal to 85. And our pooled variance, which we had calculated earlier, was equal to 20. So we're going to take the square root of that. So in our calculators, go ahead and compute 93 minus 85. Again, that's 8. And then 20, we take the square root of 20, and we get, if we round, 4.7. And our estimated D then, 8 divided by 4.7, we should get 1.79. And what does that mean? Well, what we're saying is, if we have the population of those who watched, so again, represented by, so our sample 2, or population 2, again, these are those who watched, did not watch. And their average is equal to 85. And now we have the second distribution with an average of 93, and we'll place them over here. Again, this is not always beautiful or accurate given freehand drawing. And the mu of our first distribution, those who watched, was equal to 93. Again, we know that this is equal to 8-point difference, right? In the test that they took, those who watched scored on average 8 points more than those who didn't watch as children. And now we're expressing those 8 points in standard deviation units. So the 8 points is equal to 1.79 standard deviation units. So we're moving, our shift from here to here is 1.78, almost 1.8 standard deviations, almost 2 standard deviation units. If you think of the expression of Cohen's d of z-scores, and we talk about, anything beyond 1 is considered very different. And then if someone were to say, you're 3 standard deviation units, they're saying you're very unique or different. And so here we're saying this shift is almost 2 standard deviation units. We've standardized those 8 points into what you can consider z-scores, standard deviation units. And so that's pretty significant. Remember from our table, anything above 0.8 was considered large. So here we're seeing a large effect size that watching Sesame Street as children had a huge impact on the performance of these students at the high school level. So next statistic we're going to calculate is R squared, percentage of change attributed to treatment or difference in quasi-independent variables. So our equation is same as before, t squared over t squared plus degrees of freedom. We can replace variables. Again, our T statistic was equal to 4. We're going to square that. 4 squared, and then our degrees of freedom was equal to 18 because each sample was equal to 10 individuals. So now we can solve this. 4 squared, 16. 16 plus 18, and we get 16 over 34. Our R squared is equal to 16 over 34. So in our calculators, we get a value equal to 0.47. And what does that mean? How would we express that? Excuse me. We would then indicate that 47% of the difference in academic performance is attributed to the difference in TV viewing habits. In particular, the difference in the fact that one group did watch Sesame Street as children and the other did not. So 40% of that difference, again, what we're talking about, the difference between an average of 93 compared to an average score of 85. That 47% of that difference, again, the difference is 8 points, 40% of that difference is due to the fact that they had different TV watching habits, that one group watched Sesame Street and the other did not. And according to our table for R squared, presented in the previous chapter, anything above 0.25 is considered large. So again, this is another expression of a measure of effect, another expression that there is a difference in these in this quasi-independent variable, or the quasi-independent variable conditions. One condition, they watched Sesame Street as children. The other condition, they did not. And now we're saying that this statistic supports that there is a difference and that the difference is significant. And finally, as another supporting statistic, we're going to calculate a confidence interval. And this example instructs us to compute a confidence interval at 95%. So we're going to go through the steps to do that. So the difference between sample 1 and sample 2 is used to estimate the population mean difference. The T equation is solved for the unknown population mean difference, and here's our new equation. So population 1 minus population 2 average is equal to, we're going to use the sample data as the center, the basis of our prediction. So we take the mean difference of our samples, and then we add that to the product of our T value. Again, the T is coming from the confidence set and degrees of freedom, multiplied by the estimated standard error of the mean difference. So a couple of things. Let's first, so now that we are saying there is a difference, now we want to estimate, if we were to take all possible samples from the population, or populations I should say, and compute the mean difference between their scores, we're trying to estimate what that true population mean difference would equal. That's what we want to find out. We want to calculate a range. And again, this center, right, we're going to use this sample data as the representation of that center score. And then we're going to calculate a mean difference here and a mean difference here using this equation. So again, the range is going to then be expressed that we're 95% confident that the true population mean difference, right, that's what we're calculating, falls within this particular range of values. And so again, this in the center, this is this no longer is representative of the null, because now we're talking about, we've confirmed that there is a true difference. And again, this comes from M1 minus M2. And I think what I will do in the next slide is just use that at the center to not confuse you, but ultimately we recognize and should not lose sight of the fact that those values, those sample values, are representative of the population values. And before we do the calculations, a couple of points that we should point out and focus on in terms of what the confidence interval does for us. So it's an estimation can provide an indication of the size of the treatment effect, again, because we're calculating what we would expect the true population mean difference to equal. The estimation can provide an indication of the significance of the effect. Again, it is seen as a supporting statistic to report alongside of your conclusions. If the interval contains 0, okay, so if the interval contains 0, then it is not a significant effect. Again, 0, mu1 minus mu2 is equal to 0. Where did we see that? The null hypothesis. So again, if we calculate a range, a confidence interval, and it is inclusive of the value of 0, then we're saying that the null is true. So we hope that our interval does not include the value that represents the null, which in this case is equal to 0. If the interval does not contain 0, the treatment effect was significant. So again, we can see how we can interpret this range of values that we're going to compute. So this is our equation. We're calculating the anticipated population mean difference, and using the sample data as the center of that range of predicted values. So let's just replace variables. What do we know? So again, we're calculating what we anticipate the true population mean to equal. Our sample 1 mean was equal to 93. Our second sample mean was equal to 85. We're going to add and subtract the product of our t value. Again, a caution here, that is not your t statistic. This is t value comes from our t table when we look up the value given the percentage of confidence and degrees of freedom. So we'll come back to that. We don't know what that is right now. And our estimated standard error of the mean difference we calculated previously was equal to 2. So now to find what this t value is equal to, again, we had set 95 as our confidence interval, and we need our degrees of freedom. Degrees of freedom for this example is equal to 18. So what we're saying is that we're 95% confident that the true population mean difference will reside within this calculated value. Again, we have 5% represented in both tails. So the first step is to compute that, transform that 5% into a proportion so we can enter our t-table. So that's 0.05. So we're going to use this and degrees of freedom. And because we're calculating a value below the center and above, we recognize it's two tails that we're utilizing. We're going to use the two-tailed tier of our t-table. Okay, so again, the values necessary to find t is our degrees of freedom, which is equal to 18, and given the 95% confidence interval, we're going to find 5% in the tails, and we're using the two-tailed process because there are two tails that we are accounting for. So here's the 5%, and then degrees of freedom, 18 here. So we're just going to see where those intersect with one another, and we find that t is equal to 2.101. Okay, so now we have figured out what our t value is equal to, so I'm going to put that in our equation here. So that's 2.101 multiplied by 2. And again, the positive negative here is so that we are able to calculate a mean difference to the left of the center and to the right of the center. I'm going to clean up some more of this information so I have ample room to write everything that I need to. Okay, and what I've done here is in the center I've represented sample 1 mean minus sample 2 mean is equal to 8. We know that that's the sample mean difference. And now we're going to calculate a range of what we anticipate the true population mean difference to equal. So mu1, let me rewrite that. Mu1 minus mu2 is equal to 93 minus 85 was 8, plus or minus, and now our calculators compute the product of 2.101 multiplied by 2. And we should get 4.202. So we're going to add that to 8 and subtract it from 8 to find what we would anticipate the true population mean difference to the range in which we expect it to fall. So on the high end, we calculate 12.202. And on the lower end, again, 8 minus 4.202, we get 3.798. And again, these values came from taking 8 and adding that product of 4.202 and subtracting that product of 4.202. And now this is the range of the true population mean difference that we would anticipate. Again, given the sample data, it was a good starting point. Our samples are representative of our populations, but we know they're not perfect. And so now what we're trying to estimate is if we had access to both populations, computed the average for those populations. Again, we're talking about the average academic score for those who watched Sesame Street opposed to those who didn't. And we took those true population means if we had access to them and took one minus the second one. the difference that we would anticipate would fall within this range of 3.798 and 12.202. And in fact, we're saying we're 95% confident that if we had access to both populations and we're able to compute the mean difference between those two populations, we're 95% confident that the mean difference would equal and fall within the range of 3.798 to 12.202. So again, it's just another additional measure of effect size. And notice, again, on a previous slide, we said if that range includes 0, then there is no significant effect. 0 is not in that range. So we are confident that there is a true effect, and that watching Sesame Street as a child does have an impact on your academic success as a high school student. So figure 10.5 is an illustration of what I just mentioned. Again, the range, again here, was based on M1 minus M2. It's a good starting point of what we would anticipate the true population mean to equal. And these are the values that we calculated in the previous slide. And the null, right, the null says that that mean difference would equal 0. And notice it doesn't fall within that range. And so this means we are pretty happy. We're confident that we have not engaged in a type 1 error, and that we do see a significant effect or difference when comparing the conditions of this quasi-independent variable. And we'll conclude with what all of this would look like in the literature in a report. So we would report whether the difference between the two groups was significant or not. We're going to report descriptive statistics, such as the mean and standard deviation for each group. Report the T statistic and degrees of freedom. Include a probability statement, and then include our supporting statistics such as confidence interval or estimated D or R squared. So this point here would be applicable if we had generated a computer output for our statistical test. So what I'm going to focus on is the written results and then the supporting statistics to go along with the verbiage that I'm going to present. So first we're going to indicate what we did with the null. So we reject the null. The null says no difference, and we have enough evidence to reject the null. And then we could state that the results indicate that the academic success of the high school students that watched Sesame Street as children is significantly different compared to the success of high school students that did not watch Sesame Street as children. And then we would include our statistics. So our T, we had degrees of freedom in parentheses equal to 18. Our T statistic was equal to 4. Our probability statement says that there's less than a 1% probability that we would produce a mean difference equal to 8 points if the null were true. Again, the probability of obtaining a mean difference of 8 points, again, the 8 points came from 93 minus 85, that there's less than a 1% chance that that difference would be obtained if the null were true. In other words, we're saying that it's not due to chance that we got such a large mean difference. And then I'm going to include all of the statistics that we produced, D was equal to 1.79, R squared was equal to 0.47, 0.47, and then our 95% confidence interval, which would be reported as the range computed. And just to point out that technically we would not see all of these supporting statistics included. The researcher would include one, so we would verbally cite what we did with the null, explain what we tested, what the results indicate, and then include our T statistic, degrees of freedom, our probability statement, and then one of these three measures of effect to support our concluding statement. Now, given the length of this video, I apologize that it's gone so long. I'm going to end it, and in the next video, give you an example of a one-tailed hypothesis test using the t-test for two independent sample means, and then also discuss some of the assumptions required to engage in a a t-test for two independent sample means.